Greetings and welcome you again to this course on CFD. Last two lectures we had seen finite volume strategy for diffusion equation. We did that in detail. We took an example problem and illustrated with the example problem including in the implementation of boundary conditions. And last class we had also seen how to extend explanation that we did for one dimensional to two dimensional as well as three dimensional. Today's class will particularly focus on convection as well as diffusion term included in the equation. Just for the sake of completeness, we will repeat again the terminologies used in finite volume strategy. This is a mesh that we have defined for one dimensional. P is a node of interest, east node and west node. East of east node is given by EE and west of west node is given by WW. Distance between the point of interest P and the respective nodes are given by corresponding subscript. In this case, for example, distance between node P and node W, because it is 1D, it is delta x and with the subscript P W. So, it is delta x P W. Similarly, distance between node and the corresponding face, in this case for example, the face W on the left side is given by delta x and corresponding subscript P and small case letter W. You can follow for other face as well as for other node. So, in the general Navier-Stokes equation, if you neglect time dependent terms, then you get convection term on the left side, diffusion term on the right side plus any source term, and that is what is shown here. So, divergence of rho u phi equal to divergence of gamma gradient phi plus source term. Phi is a variable, any property, gamma is a diffusion coefficient and u is a velocity vector. Now, if you do the control volume integration for this equation, it will result in this form: integration over A n dot rho phi u dA. So, this gives the flux, convective flux equal to diffusion on the right hand side plus source term, the second term on the right hand side. So, the RHS accounts for net diffusive flux and the generation or the dissection of phi. The LHS accounts for net convective flux. We should know how to convert the volume integral into surface integral. Main difference between convection term and diffusion term: convection term influences only in the flow direction, whereas diffusion term influences in any direction where there is a gradient, and this difference in the behavior needs special attention when you are evaluating variables at phases and to be used in convection term differently from diffusion term. Let us take an example situation. Again we take one dimensional situation. So, steady one dimensional convection diffusion. For the sake of simplicity, again we do not have a source term. So, we write down the equation as given here: d phi by dx of rho u phi plus d phi by dx of gamma d phi by dx. Because it is one dimensional, we write in differential form. Again we reproduce terminologies and mesh arrangement. So, considering the same discretization as in 1D diffusion equation, integrating this equation over the control volume will result in final form like this: rho u phi evaluated the east phase minus rho u phi evaluated the west phase equal to gamma a d phi by dx evaluated the east phase minus gamma A d phi by dx evaluated the west phase. If you observe here, the right side terms are already familiar to you. We did that in detail when we did 1D diffusion equation. So, this quantity are to be evaluated as east phase and west phase. Here on the left side you have a convection flux that has variable to be evaluated at east phase and west phase, whereas the right side it has a derivative of the variable to be evaluated at the east phase and west phase. So, you understand we have additional complexity when we deal with convection term. If this convection is written for say phi as a variable, u as a variable for phi, then it becomes rho u phi u and rho u evaluated at east phase and west phase. So, we define separately convective flux and use a symbol letter F subscript C for convective flux equal to rho into u, and diffusive flux F subscript D gamma by delta x. Now, using this symbol, the discretized equation is rewritten as F c A into phi evaluated at the east phase minus F c A into phi evaluated at the west phase equal to similar rearrangement on right side for diffusion term. Now, we did in the diffusion equation central differentiation type of approximation to get delta phi at phases. We follow the same here also. So, employing central differentiation scheme to evaluate delta phi at control volume phases for diffusive flux, and for simplicity's sake we assume area is the same. So, A e equal to A w is the same as A, which means all the area term from this equation will get cancelled. So, you get finally expression as shown here, F c evaluated at the east phase, phi evaluated at the east phase minus F c evaluated at the west phase, phi evaluated at the west phase equal to, we followed central differentiation type of approximation and we already defined F d as delta x. So, corresponding delta x term goes there. So, we get final form as shown here. We have additional term, that is the variable phi itself at control volume phases. So, for a uniform grid arrangement, again linear type of interpolation can be used. So, phi evaluated at the east phase, phi defined at the east phase is evaluated from pi at node of interest P and pi at E. So, it is a linear approximation or central type approximation. Similarly, for other quantity phi that is required at the west phase is related to phi variable available at node P and W. Upon substituting this replacement in the discretized equation, then we get finally this equation as shown here. So, phi is actually replaced correspondingly. So, this is for phi e and this term is for phi w, and on the right side we have already written for diffusion flux. We will have to do some more arithmetic, that is F d w minus F c w by 2 plus F d e plus F c e by 2, and all these are coefficients multiplying phi p. In the previous equation we collect all coefficient, that is multiplying the variable phi at p and we rearrange, then we get this form. So, this is the node of interest, and that is unknown and that is retained on the left hand side. Then on the right hand side similarly for west as well as east variable coefficients are respectively written. As we said many times before, P is the node of interest, and in this case for 1D the node of interest will run from left to right. We do one more rearrangement, we will understand why we are doing this rearrangement. So, this FDW is retained and we would like to have FCW by 2 with the minus sign. So, what do? We add FCW full term and then subtract. So, eventually this FCW by 2 positive and minus FCW which is added newly will result in minus FCW by 2. Okay. Similarly, we have only FCE by 2 and we add FCE newly and subtract. So, if you put this term, that is minus FCE by 2 plus FCE, the original positive FCE by 2 is maintained. This is for some convenient sake, you will understand, equated to terms on the right hand side. Now, if you observe terms on the right hand side, for example, coefficients for phi at W, it has a term FDW plus FCW by 2 and you are able to observe similar term appearing as one of the coefficient on the left side, right. So, this is FDW plus FCW by 2, that is one term on the left side which is same as coefficient term for phi at W. Similarly, the second term on the right side which is written as coefficient for phi at east face at east node FDE minus FCE by 2, again you are able to observe this coefficient appears as one of the term in the coefficient for phi p as shown here. Okay. And these are new term we have added purposely to get coefficient term as shown here and similar to coefficient term on the right side. Again you recall how we did for diffusion equation. In diffusion equation we had finally written a form AP, that is coefficient for node of interest P is a summation of coefficients from the surrounding nodes, and that is the format we are getting it here also. That is why we have to do this rearranging. Rearranging the coefficient as we did in diffusion equation. So, we have AE as defined FD evaluated at west face plus FCW by 2, then AW written as shown here. So, you are able to write coefficient for AP as sum of coefficient for west node, east node and this subtraction. So, in essence you observe that if you have a diffusion equation and you have written a code for diffusion equation, now you want to improve the code or augment the code to include convection term, then all that you have to do is just add this extra terms for AP, extra terms for the respective neighboring nodes. So, in this case AW and AE. So, this is how the code is developed from one module to the next module. As I mentioned before, node P runs from left to right. So, if you run node P from left to right, in this case it is 1D. So, we say it is running from left to right. In the case of 2D, you will also run from in the y direction from the top to bottom and 3D respectively for the third direction. If you do so, then you will get set of linear algebraic equation. Then you have to have a procedure for inverting the matrix. For the example illustration that we have taken, we have considered without a source term, and it is possible to include source term, and that source term will go as a known term and it will go to the right side of the equation. And near the boundaries, so in this case for example 1D case, left boundary node near the left boundary, there is no west node, hence coefficient A w goes to 0. Similarly, node near the right boundary, there is no east node, hence coefficient A e goes to 0. This is something that we had seen in the diffusion equation, and they do not change when you include convection term also. The boundary conditions are reflected in the source term appropriately. This again we had seen in the illustration that we used to explain diffusion equation. The temperature term, which is enforced as a boundary condition, appears on the right side of the equation. Now, we explain all this for a uniform spacing. Variable phi appears in the convective flux and the derivative of the variable appears in the diffusive flux. So, we need to evaluate variable as well as derivative at phase, and we have demonstrated with the help of a uniform mesh. Now, in the case of non-equal spacing, we also have to know how to do for non-equal spacing, because in a practical situation you do not have a luxury of having a uniform spacing mesh throughout your domain. So, for non-uniform spacing, so this is the terminology or mesh arrangement that we have used for uniform mesh, and we have phi evaluated using central approximation or linear type of approximation. For non-uniform grids, we have to have appropriate weightage procedure to account for contribution from respective nodes. So, what is shown here, it is illustration. We have one control volume as shown with the node marked as 1, then another control volume with the node marked as 2, then we have also point of interest P, and the control volume for P will run from 1 to 2, budding 1 to 2. In such case, suppose you want to find for P say variable at P, then you can have weighted average procedure as shown here. Phi at P is evaluated based on area multiplying a variable at other node. Similarly, area for the second control volume multiplying variable at that another control volume, and total and summation of average summation of area. So, we have been talking about convective flux and variable phi present in the convective flux, and how to get that variable evaluated at control, how to get variable evaluated at the phase. Now, these convective terms are nonlinear in nature, and it also multiplies its derivative. They are mostly influenced by direction of the flow. So, we have to have the correct evaluation of the variable and its derivative at that phase, which is very important as it affects accuracy and solution procedure. They should obviously represent the correct flow physics, and it decides accuracy as well as stability, and we will observe with an example graph later how it affects accuracy. So, we are going to discuss 5 approximation scheme in detail. They are central approximation, pure upwinding approximation, hybrid scheme, power law scheme, and quick approximation. First, we will take central scheme. We have already seen the central scheme. The central scheme, as we noticed earlier, it takes equal weightage from the neighboring nodes. Because of its nature, it is unable to identify the direction of the flow. So, for example, in this illustration that is shown here, the flow is from left to right as marked here. We know the variable value at west node and node of interest P. Then the CD scheme assumes equal influencing from either side. That means, phi at its phase w takes a value of phi at p and phi at w and divide by 2. Okay. That is for the uniform spacing. Of course, if it is a non uniform spacing, you take into account the weightages. Similarly, for another situation, if the flow happens to be from right to left, then phi at east phase is evaluated based on phi at east node and phi at p node. Okay. Now, why do you have this flow direction changing? That may be a curious question. We will reproduce this slide that we had seen in week 1 lecture. This is a test case problem, flow through a backward facing step, and in this case the inflow is here and it is a fully developed parabolic velocity profile, and the top side is a channel wall and bottom side there is a step and then there is a channel wall. Now, as you have explained before, at the corner, at this tip of the corner, flow separates and then it comes and reattaches on the bottom wall at some distance. Where it attaches, it depends on the flow condition, Reynolds number and so on. Now, the question that is important is what is happening to this region. This is a recirculation zone and there is a eddy and flow recirculating in this region. That means, if you define x and y coordinate orientation to be as shown here, then you can observe with respect to the coordinate definition that you have chosen, for some part x u velocity is positive and for some part u velocity is negative. So, this is a main reason why you have to have a scheme which takes into account the convection of the flow also. There is another situation for the same problem, depending on the Reynolds number and depending on the flow condition, for the same geometry you may have a situation where there is a secondary bubble formation on the top wall. Here also you can observe for some part of the location it is u that is positive, that is going from left to right, and for some part of the location u is negative, that is going from right to left, and this u positive or u negative depends on your coordinate definition. So, for the coordinate definition that you have chosen, I have explained u positive and u negative. Of course, there is a difficulty near this boundary where it switches immediately between positive to negative. So, such difficulty or such change of flow direction is very common in practical engineering problem. Hence, we have to look in detail how to deal that situation. I conclude today's class here, and we will look into details about different methods of interpolation in the next class. Thank you.